All right. So we're happy to welcome Pat Clancy from McMaster University. Pat got his PhD at McMaster University, doing some X-ray, neutron and mostly X-ray scattering studies of like spin spirals chains and things like this. And then he came to University of Toronto as a Banting fellow. Yeah, very prestigious Canadian postdoctoral fellowship. Where he did a lot of nice RIXS work and also mentored a young neutron scatterer who's currently doing his PhD there. Told him, where to get the best, mostly where to get like the best food around synchrotrons.
So really important stuff.
Yeah, really important stuff. I'm talking about myself. After Toronto, you moved as a faculty at Trent, and then back as a faculty at McMaster, where he's continuing a lot of really nice X-ray experiments, and also helping run Canada's most powerful research reactor at McMaster University. They have universities with nuclear reactors, so that's great. Thanks, Pat.
Yeah. Well, thanks very much for the introduction, and thanks everyone for coming today. It's a real pleasure to be here. This is my first time in Rhode Island, and I've had some great conversations with people today. So what I'm going to be talking about today is some recent experimental work that my group has done looking at spin orbit driven physics in ruthenium-based quantum magnets, and I can't resist using the stick. And so in particular, sort of two example compounds here. This one, which is a ruthenium double perovskite, which is going to be a candidate for excitonic magnetism, and this one over here, which is a ruthenium cluster magnet that's going to show us some sort of interesting delocalized or itinerant behavior. And so this is going to be mostly an inelastic X-ray scattering story with a little bit of neutron spectroscopy as well. Okay. But before I get into that, I did want to start with some neutron propaganda. And so maybe you haven't heard of McMaster or don't know where we are. We're a city about halfway in between Toronto and Niagara Falls, so pretty close to the border with New York State. And one of our claims to fame is the fact that we have a university-based nuclear reactor. So this is our reactor here. It is a literal stone's throw from the physics building, which is just over here. And this is what we call a swimming pool type reactor. So it's a 5 megawatt research reactor. You can see the outside of the building here or the inside of the building here. And this is really a multi-purpose research facility. It's used to make medical isotopes. So about half of the world's supply of iodine-125, which is used for thyroid and prostate cancer treatments, comes out of this reactor. We also do neutron radiography, sort of neutron irradiations, but more importantly, material science using neutron beams. So this is not a new facility. It's been running more or less continuously since the late 1950s. But about 8 years ago, our large national neutron source at Chalk River, the NRU reactor, closed down, and we became the most intense source of neutron beams in the country. Not the way you want to get to number one, but a win's a win.
So what do you do with all the extra power? What do you do with the power outside of generating isotopes?
So we don't do anything. We don't heat anything. We just dissipate the heat. So we only make neutrons at the reactor there. It is one of the best places where you can go to actually see the Cherenkov radiation, though, and there are public tours. So if you're ever in the neighborhood, you should come and see this. But from a science point of view, what we're most interested in are the beam ports. So there are 6 of these ports. You can see maybe them coming radially out from the core there. And at the moment, we are sort of in this process of building out our reactor into a national user facility. So about a year and a half ago, we launched what we're calling the Canadian Neutron Beam Lab at McMaster. At the moment, this is sort of what things look like now. If you go down to the beam port floor, we have these 6 ports. 2 of them are used for neutron radiography by a commercial company called NRAY. One is used for sort of chemical analysis using prompt gamma or neutron activation. One is being built to do positron annihilation lifetime spectroscopy. And then we've got these 2 beamlines in green and blue here, which are neutron scattering beamlines. Okay? The good news is We have money to expand pretty significantly over the next 4 years. And so what we're hoping is by the end of 2029, we'll have 3 additional instruments that'll let us do diffraction measurements on a variety of different samples. So there'll be a new reflectometer to look at films and interfaces, an optimized powder diffractometer, sort of general purpose single crystal instrument, our SANS instrument, and then an industrial diffractometer we'll be able to use to do residual stress measurements. So not just stuff that's good for quantum materials, but for a variety of different areas of material science. Okay. So just quickly to show you what the instruments look like at the moment, this is our all-purpose diffractometer. This is sort of our workhorse instrument at the moment. It does a little bit of everything, single crystal, powder diffraction, spectroscopy, although pretty slowly, incoherent scattering to look at hydrogen materials, attenuation. It has a triple axis configuration here. More recently, it's been operating in this high efficiency diffraction mode using this 80-degree detector that we inherited from Chalk River. And we're sort of building up our stock of sample environments to look at structural and magnetic changes over a broad range of temperatures. Okay? We also have this small angle scattering beamline, which is great if you're interested in more complicated nanostructured materials. Can be good for quantum materials or high temperature superconductors, but also if you like biological materials, soft matter, whether that's membranes or polymers and plastics, there's a variety of new types of science you can do here as well. Okay, so last part of the plug, if you are interested in doing experiments, we do mail in. We're always happy to have people come and visit us. We even have a QR code. That's how serious we are. So if you are curious, please let me know. We're happy to run just about anything to give you an idea of what the data looks like. And we have sort of an ongoing call for proposals. There you go. Plug over. The proposal form is actually pretty quick. If you get bored, you can fill out a proposal. You'll be done before the end of the talk. Okay, so switching gears, the sort of science part of today's talk, I'm going to be talking about spin orbit driven materials. I know there's folks here who are already interested and are working on 4D and 5D transition metal oxides. For those of you who aren't, the reason that we're interested in this family of materials is it's one avenue that we can take if we're trying to look for new and exotic physics. So new quantum states that we get because of the presence of strong spin orbit coupling. Okay, so in general, as you move down the periodic table from your more common 3D transition metals, your iron, cobalt, nickel, copper magnets, as you go down here, your electronic wave functions become broader, more spatially extended. The electronic correlation effects become weaker. The spin orbit coupling, which is sort of roughly going like the atomic number, that becomes larger. And so you reach a place in these 4D and 5D transition metals where you have about 3 or 4 different energy scales that are all of about the same order of magnitude. Okay? So you get this interesting balance between correlations, crystal electric field, Hund's coupling, and spin orbit coupling. So here's a sort of cartoon phase diagram sort of showing you the kind of states that you can get. This is plotted as a function of spin orbit coupling along the horizontal, electronic correlations along the vertical, and you can see that you can get sort of topological insulators, topological semi-metals as you go out here, or the really interesting stuff happens when you ramp up both lambda and U when you get up here. This spin orbit coupled regime where we have spin liquids, wild semi-metals, topological non-insulators, and all sorts of exotic states. Okay? So this is a field that people have been working on for some time now. This was a hot topic when I started my postdoc at Toronto. Originally, a lot of the interest in these materials was driven by compounds that were based on this D5 electronic configuration. Okay, so transition metals like iridium or ruthenium, where you can have these 5 valence electrons. Most famous example, I think, still maybe, of a new state that we get because of the strong spin orbit coupling is the J-effective 1/2 spin orbital non-insulator. Okay, so this is an unusual electronic state you get because of the strong spin orbit coupling. Right, we mentioned as you go down the periodic table, the electronic correlations become weaker, so you don't have enough U to give you a normal mod insulating state. But instead, you get the combined effects of their crystal electric field, and then this spin-orbit coupling can split your T2G levels into a lower J-effective 3/2 manifold, an upper J-effective 1/2 manifold, and then here you have a half-filled J-effective 1/2 band. Even a pretty weak U is enough to open up this insulating gap, which is exactly what's seen in materials like strontium iridium oxide. Okay, so this is the canonical example of a spin-orbital monoinsulator. So if that's the most famous example of spin-orbit-driven physics, a close second, maybe now, the first thing people think about, not an unusual electronic state, but an unusual magnetic state. Okay? So one of the things that happens in this strong spin-orbit regime is that your spin and orbital angular momentum are strongly coupled. They become heavily entangled, and so instead of treating these separately, we have to be thinking about them in terms of total effective angular momentum. Okay? So for these D5 configurations, you get J-effective 1/2 isospins, and the interactions between these isospins are strongly geometry dependent. Okay? And so if you have materials that are based on edge-sharing octahedral crystal structures, okay, so if you have this kind of bond geometry here, we've got a transition metal, and then oxygens here connecting it, then the magnetic interactions, the super exchange, runs through these transition metal oxygen transition metal pathways here, and the super exchange through the upper and lower pathways here cancel out through these bonds. Your normal Heisenberg interactions disappear, and you get these really unusual bond-directional interactions that we call Kitaev interactions. Okay? And when you put these onto real lattices, like the honeycomb lattice here, okay, this is a nice edge-sharing octahedral crystal structure. Then with the strong spin-orbit coupling, this bond geometry, you can get these directional Eisenberg interactions that can give you what we call a Kitaev magnet, or in some cases a Kitaev quantum spindle. Okay? All right. So one of the things that's interesting, as sort of an extension of this Kitaev story, the first Kitaev materials that people were interested in were these honeycomb lattice iridates. And the idea being that if you want an unusual spin-orbit-driven state, the best place to go is where you've got as much spin-orbit coupling as possible. So that means going to the 5D transition metals. But one of the lessons that sort of came out of more work on this is that more spin-orbit coupling isn't always better. And the best of these experimental candidates that we have for Kitaev model physics isn't actually these honeycomb iridates. It's actually a 4D transition metal compound, alpha ruthenium chloride. Okay? So I'm going to cite the seminal work of Kemp from 2014 here. And so this is another edge-sharing octahedral crystal structure here, now based on a 4D transition metal instead of a 5D transition metal. It's not a quantum spin liquid. It does order at low temperatures, but it is quite close to what we think of as this quantum spin liquid regime. And if you apply a 7 Tesla magnetic field, you can kill off this ordered state, and you get into what has been proposed as this field-induced Kitaev spin liquid regime. Okay? All right. So again, this is where a lot of interest in these spin-orbit-driven materials has been, on the D5 configuration. And so what I'm going to do in the rest of this talk is try and convince you that there's interesting stuff that happens with other electronic configurations as well. And we've got two different examples here. The first, which is going to be this double perovskite material, lanthanum, magnesium, ruthenium oxide. Okay, so this is not D5, this is going to be D4. And here we're going to have something that could be related to excitonic magnetism. And in the other case, we've got this ruthenium cluster magnet, which has these ruthenium dimers. And this is going to give us sort of an interesting model system that we can play around with to learn more about molecular orbital physics. Okay? And so I'll show you a little bit of synchrotron data, so resonant inelastic X-ray scattering measurements that were collected at NSLS2, as well as some neutron spectroscopy measurements from the Spanish neutron bridge. And I just wanted to highlight Bo Yuan here. Bo's now a research scientist, was a postdoc in my group, who really was the sort of driving force for both of these projects. Okay. So starting with our double perovskite story, if we go from this D5 configuration that we started with to a D4 configuration, this is another place where you get unusual behavior because of the strong spin-orbit coupling. Okay? So normally if we have this D4 configuration, Hund's rules would give us something that looks like this, right? If we split our transition metal D valence levels using an octahedral crystal field, we've got 4 electrons to distribute here, and we get a spin 1 state. Okay? Should be magnetic. When the spin orbit coupling becomes stronger, okay, that breaks the degeneracy of these T2D levels. And now when we fill up our levels with our first 4 electrons, the J effective 3/2 levels here are totally filled. Okay? These are totally empty. So we have something that's effectively non-magnetic. Right? This is J effective equal to 0. Right? So you're saying, why are we studying magnetic materials that have no magnetism? That's a good question. Well, it's because about 10 years ago, yes, 13 years ago now, there was a prediction that if we have these D4 type systems that seem to be non-magnetic, it's possible that they could still show an unusual form of magnetism we call excitonic magnetism, if there's a way that we can take the first excited state and drive it across the ground state. Okay? So what does this look like? If you imagine looking at the J effective non-magnetic ground state here, the first excited state is this manifold, got a triplet of J effective 1 states, then a quintet of J effective 2 up here. Okay? And if we can bring the J effective 1/2 state energy down so that it crosses the energy of the J effective 0 state here, then this can condense and we get excitonic magnetic order. Okay? So you can do this with structural distortions. Okay? That's one way to bring these energy levels down. You can also do this if you have significant magnetic interactions. Okay? So if you pick up dispersion here of this J effective 1 level here, we typically call this a spin orbit exciton. We can bring this down so that the gap becomes small. Okay? If this eventually crosses, then we're going to condense and get excitonic magnetic order around this position, Q0. Okay? So there were a number of systems that were proposed as possible candidates for this kind of magnetism. The first materials that people went to again, where you look for weird spin orbit driven things, where the spin orbit coupling is strongest. Okay? So the first stop was iridates. Now again, instead of going to iridium 4+, which is 5d5, we're looking at iridium 5+, which is 5d4. And this double perovskite crystal structure, for those of you who aren't familiar with these materials, the real advantage of this structure is that it's really easily tunable. Okay, so we have this general form A2B iridium 06, and there's a host of different elements we can put on the A site and the B site. Okay, this gives us a way to tune the moments, the lattice constants, bond angles, if you like. So we have a lot of freedom to play around here with composition. And in a number of these compounds, there are reports of magnetic order. Again, magnetic order in these materials that should, by all accounts, be non-magnetic. Okay? We actually looked at some of these materials with RIXS, and you can use RIXS as a way of mapping out these orbital energy levels. You get a nice picture here of energy transfer, and you can see these peaks where we get DD transitions from one orbital to another. And we'll talk more about this in a minute, but the key point here is that the excitonic energy gap that we're trying to close in these excitonic magnets is this gap here, okay? From E equals 0, so where our sort of ground state is, to this peak here, which corresponds to the first excited state, the spin orbit exciton, that J effective 1 state. Okay? And what you can see here is in these double perovskite iridates, this energy gap is very big. It's about 300 millielectron volts. Okay? Way too big to close just as a function of temperature or with most normal perturbations. Okay? So this excitonic magnetism picture really doesn't seem like it has much to do with these materials. The gap is just way too high to close for normal circumstances. And actually, if you go out and measure a bunch of these different materials, so you can see here we've got a variety of different A sites, barium, strontium, lanthanum as well, and B sites. Here you can tune the crystal structure from cubic to monoclinic, so you can introduce all these distortions. And maybe it's hard to tell, but there's almost no difference between any of these. Okay? So the energy levels look the same. They're very insensitive to any structural details. So what we think is that any of these reports of unexpected magnetic order are likely coming from structural defects or magnetic impurities. Okay? So one of the things that you can get in the structure is anti-site disorder, which can play around with your oxidation states. So double perovskite iridates, not the way to solve this problem. So people went away from this large spin orbit regime to the 4D transition belts, okay? Going down to a smaller spin orbit energy scale. If you have less spin orbit coupling, it reduces the size of this gap, makes it easier to close the gap to condense this effective one state. Okay? And the first experimental realization of this excitonic magnetism was ruthenate, calcium ruthenate 214. Okay? 4D4 system, and you can look, again, you can see these energy levels, and you can see the magnetic order that corresponds to these excitons formed. Okay? So that's great, except for the fact that if we look at the crystal structure from X-ray diffraction, or if we look at these energy levels from RIXS, what we find is that the structure is very highly distorted. Okay? And when we distort the local environment around these rutheniums, we break up the J1 levels. Okay? And so instead of condensing this triplet, we're actually condensing this JZ equals plus or minus 1/2 nanovolt. Okay? So it's still excitonic magnetism, but it's not the sort of Calulan picture that we were maybe hoping to find. Okay? So what we're really looking for is a less distorted version of this, which will still give us the same physics. So, are there other materials that we can look at? Well, the good news is that there are other ruthenates out there. And we've got an antifluorite, potassium, ruthenium chloride, as well as this double perovskite, lanthanum magnesium, ruthenium oxide. So we're going to focus on lanthanum magnesium ruthenium oxide, or LMRO. This is a sort of closer look at the crystal structure. So we've got ruthenium here at the center of an oxygen octahedra. You can see that these are corner-sharing octahedra, but you've got non-magnetic magnesium octahedra here as the nearest neighbors. Okay, so these are pretty well-separated octahedra here. There is a little bit of an axial distortion here. So two of these ruthenium-oxygen bond lengths are a little shorter than the others. You can imagine the octahedra sort of squished. And more importantly for us, the susceptibility that's been reported for this compound has identified it as having a non-magnetic singlet ground state. Okay, so it has weak Van Vleck-looking magnetism that's a little bit masked by impurity effects. So again, because of the possibility of swapping some of these lanthanum and magnesium ions here, you do end up with some non-magnetic or magnetic impurities. Typically, it's sort of around the 2 or 3% level. Okay, so there are some free spins here, but most of the spins we think are non-magnetic. So we're going to look at this in a bit more detail, taking a sort of detour into the experimental methods that we use. I know there's at least some people in the audience who actually do these resonant inelastic X-ray scattering measurements, so maybe you're already familiar with this, but it turns out that if you want to do inelastic scattering with X-rays, it's not that easy to do. You sort of get spoiled if you're used to doing inelastic scattering. And so what we're doing here are resonant inelastic X-ray scattering measurements. The resonant part just telling us that we're tuning the incident energy of our X-ray beam to an atomic absorption edge associated with one of the elements in our sample. In this case, ruthenium. we're going to go to a particular edge, this M3 edge, and this ends up being a soft X-ray energy. And so there's only one beamline in North America we can do that. That's this beamline 6, which is an NSLS2. Okay? So this is an instrument that is great for these low energy inelastic X-ray scattering measurements. What kind of experiments you can do really depends on what elements are in your samples. For this energy range, if you have materials based on 3D transition metals, you can do L-edge RIXS. If you have oxygen, you can do K-edge RIXS. And for 4D transition metals like ruthenium, you can do these M-edge experiments. Okay? Which edge you go to will define which selection rules are going to apply in your experiment, or whether you're directly probing the valence levels or not. Okay? The energy resolution for RIXS is typically on the order of tens of milli-electron volts, okay? Which does not sound that impressive until you realize that the incident energies are about 10 to the 5 times higher than that. So as a relative energy resolution, these instruments are really amazing. And so 6 in particular, to get this high energy resolution, 1 part in 10 to the 5, has a 15-meter moving spectrometer arm, which has to be controlled with incredible sort of sub-millimeter precision. So it's a very neat instrument, and so big that it requires its own addition to the ring here. It's back there.
So it's angle resolved. It's rotating on this. It's rotating on this.
Yeah. So it is. It's pretty impressive. There's birds that live in the hutch. It's like an aircraft here. Okay. So for people who do these measurements, normally if you're studying magnetic systems, you don't want to be doing this at the M edge. Okay? So this is a relatively new way to study these 4D transition metals. Normally, you would like to go to these L edges. Okay? This is going directly from the core electron levels to the valence levels here. And the L edge RIXS has a high resonant enhancement and a big scattering cross-section. Okay? K edge up here is not as great because you're not directly probing the valence levels for these transition metals. Okay? M edge also gets you the valence levels, but has a much smaller cross-section. Okay? And so the counting times become very, very long. You have to worry about trying to see these little inelastic features compared to a stronger elastic signal, and the energy dependence can be a little more complicated. The advantage you get is when you move down to these smaller incident energies, the energy resolution does become better. Okay, so it's a little bit of a trade-off, but these are measurements that are now possible. And actually, the first measurements at the MX that we recorded were for ruthenium chloride about 5 years ago by Ken and my old group at Toronto. Okay, so let's see what we can pull out from this first set of RIXS scans here. So I should say that in order to get this high stats scan here takes us about 10 hours. The count times here, if you can see, this is photons per second, and so you're less than, in many cases, 100th of a count per second. So not a fast experiment to do. What you've got on the left here, this is a map showing a RIXS spectra here. So this is photon energy transfer as a function of incident energy. And what you can see is we are varying the incident energy here. We're going through these ruthenium resonances. And so what you see is that these inelastic features that become very sharp, very intense, this is occurring when you're getting these resonant effects. Okay? And so we've got basically a set of features that resonate here, okay, at a slightly lower incident energy than the features here. This doesn't just give us element sensitivity, it also gives us orbital sensitivity. Okay? So this gap lets us associate these features with transitions within the T2G states, and these features with T2G EG transitions. Okay? So this is a scan which is taken sort of at the peak of the resonance here. It shows us the main features we've got here, A, B, and C. Okay, and what are these associated with? Well, the strongest peak here, the lowest energy one, this is going from the J equals 0 ground state to the J equals 1 first excited state. So that's our spin orbit exciton. The second peak that we've got here is going from J equals 0 to J equals 2, okay, to our second excited state. And the third peak that we've got out here, the C peak, that's going from this ground state Hund's multiplet to the first excited Hund's multiplet. Okay? So why we want to map these out is because once we've seen where these energy levels are, we can relate these directly to the microscopic terms that go into sort of single ion picture to describe this material. Okay? So in the the strong coupling regime, these spacings, J equals 0 to J equals 1, J equals 0 to J equals 2, these are just related to the size of the spin orbit coupling. Okay? This goes like lambda over 2, this goes like 3 lambda over 2. Okay? This spacing here, this is just related to the Hund's coupling. Okay? So we're getting directly to pull out these single ion parameters. Okay? All right. So if you're looking closely at these numbers, you'll see there's a slight complication. Okay? If we're really in this strong coupling limit, what we'd expect is peaks A and B here should be at a 3-to-1 ratio, whereas what we measure in practice is actually about 5-to-1. Okay? And this is because we have some other terms that are entering into our single line picture that are complicating things a little bit more. Okay? So quick digression here before. I mentioned the calcium ruthenium oxide before. Okay? These are L3 edge RIXS measurements, okay, that were done. You can see the peaks are pretty broad here. Okay? That's just a side effect of the coarser energy resolution you get these ruthenium L edges. Okay. Potassium ruthenium chloride, the antifluoride that we mentioned before. This is a spectrum that looks qualitatively similar to ours. Okay, you've got a feature here, and we'll throw our lanthanum magnesium ruthenium oxide on here as well. And we can even overplot it with the potassium ruthenium chloride. And the key parameter that we might be interested from this excitonic magnetism point of view is the difference between J equals 0 and J effective 1. So how big is that spin orbit exciton gap? Okay? And when you compare the two of them here, you'll see that in the potassium ruthenium chloride, it's about a 75 MeV gap. In LMRO, it drops to about 35 MeV. Okay? So the good news, if this is what you're going after, is that this is one of the smallest measured spin orbit exciton gaps that we've got in one of these 4D transition metal systems. Small enough to the point where you might imagine being able to close the gap as a function of pressure or strain or some other tuning parameter.
What's the error in the X direction in your MEV measurement? Like how when you say 40, like say 40 MEV, how plus or minus how much?
Yeah, so it depends a little bit on the line shape. The energy resolution is about 15 MeV at the elastic line. And I would say the uncertainty is probably somewhere between 2 and 5 MeV, depending on exactly how complex the line shape is, how well separated it is. Okay. So just to talk about the single ion physics as well, what we can pull out here, the levels that we're getting here, I said are related to these microscopic terms. So they're telling you about the Hund's coupling, they're telling you about the spin orbit coupling, they're also telling you about the effect of these distortions. Okay, so if you have other crystal electric field splittings, things like trigonal distortions or aromatic distortions, these are also things that we should be sensitive to with RIXS as well. Okay? So without going into too many details, I'll just say you can calculate theoretical RIXS vector here, and you can use the position of what we called peak C before. Okay? So this was going from the ground state multiplet to the first Hund's multiplet. That lets you pick the energy scale for the Hund's coupling. Okay? You can then look at the position of some of these other features, and you can use that to set this tetragonal crystal electric field splitting. Okay. And so you can see here that with Hund's alone and none of these distortions, we've got only 2 peaks. they're definitely off of where our expected peak should be. We introduced the tetragonal crystal field distortion to get a little bit better. But you can see we're still missing some of the shoulders here on our higher features. We introduced the third distortion, this orthorhombic splitting, and we can get something that seems to match the data reasonably well. Okay. I'll say we've done neutron scattering to get a higher resolution picture of this. Okay. So these are measurements from Oak Ridge National Lab. We see, if we look more closely at this stuff going on below, about 60 millielectron volts. We see something that looks pretty blobby up here on the screen, but I'm going to try and convince you that these are two magnetic features here. You can see this is at low temperature, this is at high temperature here. You can see that this intensity has sort of disappeared. This is perhaps softened a little bit. And you can look at this in line scans by just integrating up the intensity at low Q or high Q. And so the temperature and Q dependence here lets us associate these features with magnetism. Okay? So this is showing us the magnetic excitations, which we think are associated with this spin orbit exciton. Okay? The temperature dependence here, I'm just showing you to make the case that these excitations actually soften and broaden quite a lot as we change the temperature. And this is just telling us that we have interactions here that are beyond that single line of picture. Okay? So there are more complicated things that are going on. Okay? I will jump through this only to say that when we went back to look at this sample a little bit more carefully, one of the things that you can do by changing different edges in these resonant experiments are probe different types of excitations. And one of the things that you can use RIXS for is studying vibronic coupling. Okay, so this is an electron-phonon type coupling. And if we introduce this vibronic coupling, then you can take your regular electronic excitations that we've been focusing on so far, and you basically couple these phonon sidebands, okay, because of the strong vibrational effects that you get. So these sidebands should give you some asymmetric line shape and strong temperature dependence. And this is what's been seen in this other excitonic candidate, potassium ruthenium chloride. Okay? You get an asymmetric line shape, and it has strong temperature dependence. You can tease out what part of this line shape is electronic and what's coming from the electron-phonon coupling, the vibronic piece. And you can see how that changes as a function of temperature. Right. And I'll just say when we do the same measurements on LMRO, we see with temperature and polarization dependence, a Jahn-Teller phonon mode here, and this asymmetric line shape that becomes more asymmetric at higher temperatures. And this is a signature again of this kind of vibronic coupling. Okay? So we know that the tetragonal crystal field splitting is important, but these vibronic effects also seem like they contribute as well. Okay. So maybe in the time that's left, I'm just going to tell you a little bit about this other story. So LMRO, this excitonic magnetism picture, this is all still dealing with localized ruthenium magnetism. The interesting thing about this dimer system is that this is a cluster magnet. Okay, so it's a material that's based on these ruthenium oxide dimer units. Okay, so you get these ruthenium-2 oxygen-9 building blocks. They are face-sharing octahedra, and they're pretty well separated inside the crystal structure. Okay, so this is what we call a 6H perovskite crystal structure. And you can more or less think of these as well-separated dimers. And on each dimer, we have 7 electrons. Okay, so these form, think, molecular orbitals. And like the double perovskite crystal structure, this is a very tunable crystal structure. Okay, there's a bunch of different elements that we can put on this M site here, and that can continuously tune the crystal structure, although the changes are quite small. Okay? So we're going to focus on 3 particular compounds with indium, yttrium, and lanthanum. And you can see as we move across here from one element to the other, the changes in the key bond lengths here, whether that's ruthenium-ruthenium or ruthenium oxide inside these little octahedra, these are pretty small changes. So at the most, about 1 to 2%. So what's interesting is, in spite of the fact that the structure is not changing very much at all, the magnetic properties of the compounds are very different. So in particular, the lanthanum compound here is a huge outlier. Okay? The magnetic susceptibility is much higher, and you can pull out an effective moment per dimer here, and you see that it's somewhere between 2 and 3 times larger across this large temperature range here. Okay? So we have some big anomalous changes to the magnetic properties, and the question is, how can we make sense of this? And is this a problem that we can solve with RIXS? So it'd be anticlimactic if we couldn't solve this problem with RIXS. So spoiler alert, RIXS can help us a lot here as well. We're going to do these ruthenium M-edge measurements again. Okay, so we are going to 6 again to do these soft X-ray measurements. The ruthenium M-edge, we're probing the valence levels, and again, if you look at a map here showing the resonance behavior, this is for the yttrium compound here. Here we've got a slightly larger energy range that we've measured. Again, though, you can see features that resonate at around 463 here and here, and features that resonate around 466 here and here. Okay, so these are the features that we're associating with excitations into the TGG levels, these excitations into the EG levels. Okay, so down here, this is intra-T2G excitations, this is T2G to EG, and these are charge transfer excitations. So this is taking charge from the oxygen P levels and either going to T2G or EG levels. Okay? So, as you might expect for materials that are structurally similar, a lot of the high energy stuff looks the same in all of these materials, right? So you've got peaks B, C, D here that look quite similar regardless of which of these that we're measuring. But if we focus on the low energy excitations here, so the stuff that's going on below half an electron volt, there's this really stark difference between the indium and yttrium compounds and the lanthanum. Okay? So we've got all of the spectral weight here that seems to disappear when we go from yttrium and indium to lanthanum, and the extra spectral weight that we pick up there. So again, just to label these nicely, intra-T2G, T2G to EG, and our 2 charge transfer excitations. So how can we come up with a microscopic model that describes this? Well, we're going to do a 3-band Hubbard model based on these 2-site clusters. Okay, so we're imagining that our dimer units are where all of the action is happening. And we're going to have 6 parameters here. So we've got 2 of these intradimer hopping terms. So T1, which describes this sort of axial hopping. T2, that describes this sort of planar hopping here. We've got our spin-orbit coupling, our electronic correlations, the Hund's coupling, and the trigonal crystal field splitting. Okay? To make our lives easier, we can constrain 3 of these, okay, the spin-orbit coupling, the U, and the JH, because these are parameters that really don't change very much across almost any ruthenium magnets we measure. Okay? This is always between 0.1 and 0.15 EV. U is usually around 2.5. Hund's coupling is usually around 0.3 or 0.35. Okay? So we can just lock those in place. And then we've only got 3 free parameters. T1 and T2 are 2 hopping terms, and this trigonal distortion. Okay? So you can start by looking at the RIXS spectra in the localized limit. Okay? So before we do any complicated calculations, we want to convince ourselves that the simple model doesn't work. And so if there is no intradimer hopping for this T1 equals 0 limit, then we basically get one ruthenium that has 3 valence electrons, one that has 4 valence electrons. Okay? And in the D4 case, we get this splitting as before into J equals 0, 1, and 2. Here it's J effective 3 halves and 1 half. And we can look at the resulting RIXS spectra here. You can see that you get 1 band excitations here, 1 band here. This does not look like what we're measuring. Okay? The localized model is clearly insufficient. Okay? We get large separation between the transitions within this ground state multiplet and the excited Hund's multiplet. These ones, the energies are set by lambda. These ones, the energy is set by the Huns's Okay. We can introduce small t1. So turn on the hopping, but keep it small. And what you can see is that, again, we can play around with the size of this trigonal crystal field splitting. Okay, so that was the key to describing the LMRO in the last story. But here you can see that the RIXS spectrum varies smoothly across here for either positive or negative crystal field splitting, so either stretching or compressing our octahedra. And in no case here do we find a way to suppress these low energy states here. Okay, so none of these looks like our lanthanum data, which is shown in the book. Okay, so the fact that this is smooth, the fact that we always get our 2 peaks below 1 EV, this is something that's inconsistent. If we turn up T1, so now instead of being 0.1, if we set it to be 0.75, or if we look at what happens if we just vary this smoothly from 0 to 1 EV, you can see that the hopping has a huge effect on where this low-lying spectral weight is. And as we increase this, it moves upwards and actually overlaps with our higher energy spectral weight at around 0.75, where our 2 peaks finally become 1. Okay? So now we have something that looks like our lanthanum data. And so if we lock T1 in here, then we can play around with the size of that trigonal crystal field splitting. And what you see is that in this high hopping regime, we have this rapid transition here where we get this sharp change in the nature of the RIXS spectra. Okay? So if we pick parameters here, we're calling this point I, or point II, or 1 and 2, then we can simulate the RIXS spectra, so no extra parameters added here, except an overall amplitude, and we get something that looks like lanthanum, something that looks like yttrium and indium. Okay? So this is pretty good without adding too many extra bells and whistles. Okay? So the punchline here is that in this localized regime, we can't explain our cluster magnet. We need to add the hopping. We need to move into this more itinerant or delocalized region where things are really dominated by the big intersite hopping. And once we're in this big hopping regime, we can get this electronic transition because our molecular orbital state is fragile. Okay? Turns out that we also need a small-ish spin-orbit coupling to give us this kind of tunability. Right? So if you go to the iridium versions of this compound, so there's a barium-3m iridium-209, you don't see these kind of transitions, like in the double perovskite case. All of these systems are locked in this spin-orbit dominated regime, where it doesn't matter what you're doing with the fine structural details, the states always look the same. Okay? So things are much more interesting and much more tunable when you go to this intermediate 4D limit. Okay? So this is just calculations that sort of make that point. We're just comparing for different spin-orbit coupling sizes. This is the typical ruthenium value. This is the typical iridium value. And again, here, you can see the rapid transition over here in the iridium case. Okay. All right. And so the last thing I'll say is, if we take these parameters from our microscopic model, from points 1 and 2, we can calculate an effective moment size. Right? Qualitatively, we get something that actually describes the difference between these compounds pretty well. Okay, we get a big moment limit, small moment limit here, and the model at least gets the general features. Quantitative agreement, you can see here, is still a little lacking, but again, this is a model that only has 6 parameters, right? So if we add some interdimer interactions, stuff that accounts for some of these covalency or hybridization effects, you can imagine that this picture could get more precise, but also much more complicated. Okay, so that's sort of the end of what I was hoping to talk about here. And so the punchline here that I'd like to leave you with, when we think about where interesting spin-orbit physics is found, I'd make the case that even though there's less spin-orbit coupling to work with here, these 4D transition metals can actually be as interesting or more interesting because they give you a regime set of materials that are more easily tunable. Okay, so you get spin overturning states, but ones which are much more flexible in terms of the kind of perturbations that we have to use in the lab. We had this lanthanum magnesium ruthenium oxide double perovskite, okay, which gave us a small spin orbit exciton gap with the prospect of tuning to get into this excitonic magnetic state. We had the ruthenium cluster magnet, which gave us the tunable molecular orbital physics. We got this electronic transition that was driven by the combination of large inner site hopping, small spin orbit, and then these very small changes in local structure. And lastly, from an experimental point of view, these RIXS experiments in general are not easy. The MEdge experiments are even harder because the intensities are so much weaker. But if you have these 4D transition metal materials, there's really a lot of interesting information that you can pull out here, and a lot of parameters that are hard to get in other ways. Okay, so I'll leave you here with an acknowledgement for Bo and graduate students who did most of these experiments, and happy to take any questions you have. Thanks.
So, so you said there's clearly some electronic transition happening. But do you know anything about the nature of that electronic transition other than something is happening in RIXS? Is it like an electronic pneumatic? Is it something like charged? I don't know. What would I call the new phase?
Yeah, so it's I don't have a great answer for you there, other than the sense that you're rearranging these, you're shifting around this low energy spectral wave, so you're changing the shape of these d orbitals, and this was initially, people had tried to attribute this to a system where you had full molecular orbital and half molecular orbitals forming. Okay, so the idea was the lanthanum was one where you had molecular orbitals go along both directions. In the other case, it was only along one direction. That's not consistent with this, right? This is telling us that we're always in this molecular orbital regime, but that you're changing the position of these molecular orbitals as you're tuning the trigonal crystal field stuff. Yeah, it's not telling you about pneumatic order.
Sure. I see.
I think you skipped over this slide quickly, but I wanted to ask about if there's any evidence for a dispersion of the exciton in the double perovskite.
So I skipped over it quickly because sometimes you can model something with spin wave theory, even if it's not clear that you should model it with spin wave theory. So I would say yes, there is evidence for some dispersion here, and it's actually it ends up being difficult to capture, particularly the position of the bottom here, which we're sort of taking as the bottom of the magnetic bandwidth here. So the best fit that we can get is one that involves some pseudo spin 1/2 model. Okay, so this is not really actual JK gamma terms, but pseudo spin model that involves JK gamma and a biquadratic term, and that actually does a pretty good job if you plug these in of reproducing the magnetic susceptibility. But again, it's powder data. It's hard because it's 4D, so the form factor dies off pretty quickly, and the energy is a little higher. So I would say yes, it looks like the spin orbit exciton has some dispersion, but you really want single crystal measurements to be able to say more about it than that. Yeah. So at first we thought we needed this dispersion in order to explain, potentially some of this weird line shape here. But I think most of this is a combination of this orthorhombic crystal field splitting, but even more than that, the vibronic stuff that we saw when we went to the oxygen.
Right. So I guess what's important is that you're looking for something that has a small excitonic gap so that you could tune it to condense it.
Yeah.
What does it mean when you condense the exciton? Is it like when you if you have like a singlet ground state magnet and you apply a field and you can condense one of the triplet states in a Bose-Einstein condensation? Is it like that?
Yeah. Yeah, so you're imagining that you're getting these J-1 moments appearing when you lower that energy across the stable. So, it's normally non-magnetic. You condense them, so you get ordering of J equals 1 around this Q equals Q naught, wherever the dip in the spin orbit exciton dispersion is.
And then so in the double perovskite, so that it's the RIXS gap is about 35 MeV, but that's near the gamma. That's near Q equals 0 because there's some long wavelengths. The actual gap could be much smaller if there's a dispersion.
Yeah,
And
we're
then-
hoping.
And then so you would try to maybe apply field?
It's not clear what the easiest tuning mechanism would be, right? So you can imagine that because another way you can lower this gap is by causing structural distortion. Probably pressure and strain would be effective ways to do that. Field, of course, would help you enhance maybe the interactions there. So the problem is 30 MeV is still not nothing, right? It's still a pretty big energy scale. But
it's still 300.
It's at least workable as opposed to 75 MeV. That's high way to make it.
Right. So you think the actual excitonic gap is 30 MeV and the dispersion is not clear?
Yeah. So you're right. It could be smaller. I would hope it would be, but we know this is sort of what I'm hoping is like an upper bound. Yeah. Question back there.
Yeah. In the second group of materials, you said that they're based on this like ruthenium dimer system. What
Yes.
exactly do you mean by dimer?
So basically, just a unit that's made up of two magnetic ions, right? So dimer just means that we've got these isolated pairs. So this was supposed to be a smaller version of that crystal structure. You can see they're in gray here. At the center of each of these octahedra is a ruthenium, and they're connected. They share basically a face. And so this distance is quite small. It's about 2.5 angstroms. And so these are so close that there's really direct overlap of those ruthenium wave functions. And so you can think of it as a little 2 ruthenium unit. And instead of having the sort of isolated electronic orbitals, you get these molecular orbitals where they're sort of hybridized. Yeah.
So just back to the 30 MeV gap question. So So can you actually see? I mean, you don't have it at low enough, but can you see evidence of some kind of fluctuating magnetism? Because the base, like the ground state has no magnetic features, but then you're saying that the exciton should have something.
Yes.
So
And so in the calcium ruthenate case, you can actually see this excitonic magnetism. The catch is, there, it's not really driven by the exchange, it's driven by the big structural distortion, right? So here, we see something that still looks like this Van Vleck J equals 0 state.
Right.
We're just hoping that with the right perturbation, we could get something. There's not magnetic fluctuations that I could point to.
I see.
Yeah.
Maybe I'm just condensed matter theory brain. So like if you see this, if I could do some kind of 2-point correlation function, even though the average is 0, you would actually see that the correlation shows you that you have the magnetic order that you want. I don't know how easy that is to measure.
Yeah, but you're right. There should be fluctuations if you can get the gap small. Absolutely.
I see. But you're saying the gap is still too large.
Yeah. I don't know any evidence of anybody who's actually seen that fluctuations.
I can ask so you also you said in the RIXS data there was a Yandteller phonon in the double perovskite.
Yeah, so I jumped through that also pretty quickly.
But isn't it isn't it an orbital singlet for J equals 0?
Yes.
So does it mean it won't have a Yandteller distortion?
Yes. Yeah, sorry. Yeah, this is my fault for mixing my double perovskite systems here. Yes. So we know this is a phonon mode. It's not
But it's worth, and you see that phonon in the harmonic in the vibronic. So it's the
So if
the
you look
vibronic
at
phonon.
if you look at this splitting here, this spacing is the same as where you see the sort of asymmetric line shape there. Yeah. So we do think this is evidence of the vibronic coupling. But you're right. I should put the JT up there.
Oh, I don't know. Or maybe sometimes people talk about dynamic or like a Yanteller in the excitations.
Yeah, but it's definitely not static.
Yeah. So how important do you think vibronic coupling is for the physics of these? Because it seems to be showing up.
In a lot of
It seemed to be something that was ignored for a long time, and now it shows up everywhere.
Yeah.
And so that the lattice is really playing an active role.
Yeah.
More active than people thought before.
Yeah. So I mean, I think it depends. Your end goal is right.
Right.
Which of these states you're most interested in. But I think there's a lot of compounds that have these more complicated line shapes, and I think the vibronic coupling seems to go a long way towards explaining.
Right.
What's the energy scale of the vibrations is comparable? Is it because you're in a regime where all the couplings are basically at like 40 MeV scale or whatever?
Yeah, so we think it matters more here because the scale of the vibronic coupling is similar to the spin-orbit exciton gap, right? And how big that vibronic coupling is, like what that energy scale is, depends on the phonon modes that you're coupled to. So here, we just know these oxygen phonons are around 40 MeV or so. So in theory, you could imagine designing materials to engineer that by, if you swap from oxygen to chlorine or bromine, you should kill that.
All right. Thanks, Pat.
Yeah, thanks very much, folks.